Alright, with the tutorials dialog displayed, let's go ahead and take a quick look at where we are. Let me make this a little bit larger. So we're sort of in the middle. This is the last of the introductory tutorials. So the first time we're going to introduce calculations. This is Spectra properties and graphical models from calculations. So tutorial 7, chapter 7. We're going to look at 4 different organic molecules and do variations on the same calculation, an equilibrium geometry calculation. I'll display the calculations dialog. We'll talk about that a little bit, and I'll show you how that can be customized, and defer additional discussions to chapter 21, which really gives a full run through of the calculations dialog. Okay, so I'm not going to spend too much time talking about building anymore. We assume everyone can build in 2D or 3D. If not, go back and review the previous tutorials, and we'll just go ahead and jump in. So let's, we don't need to save this. All right, so let's build the first molecule is acrylonitrile. And we'll just build that. I'm purposefully not going to click the minimize button. Typically, I would say click this minimize button up here after any building in the 3D space. In 2D, when you move back into 3D, there's actually a minimization that happens, so things are cleaned up automatically. But the reason I didn't do that is I just want the optimization to take a little bit longer, so we can maybe watch it from the job monitor. Okay, before we submit the calculation, obviously we need to tell Spartan what it's going to do. So let's open the calculations dialog. This is the icon towards the top in the center. It's looks like a window with a gear in the lower right corner. It's just to the left of the output where we'll go and look at the results of a calculation. So either from the toolbar here or from the display, or rather the setup menu, calculations. Open the calculations dialog, and you'll see this is set to a default. The default is equilibrium geometry, ground state, gas phase, density functional with the omega B97 XD functional selected and a 631G star basis set. Okay, the system is set as neutral and 0 unpaired electrons. Nothing else selected. This is the default for everything, okay? If you want a different default, that's fine, and I'll show you where you can modify that. But this is the calculation that we're gonna run. So let me, before I hit submit, I'm just gonna say okay. And I'll go and show you under the options menu preferences. If, for example, and it's over here, it's a very terrible dialog, but over here to the right, under calculations dialog, if you click edit, this is kind of a mock calculations dialog, sort of a template. And you can go here and set up what you want for your defaults. So for example, if you love to use B3LYP with dispersion or whatever with D3, or any of maybe another 30 or so different functionals that are available from the menus, or there are a bunch that are available from type-in. You can specify what you want. If your initial task, if you always start out doing conformational searching and you want to start doing a conformational distribution, if that's your jump-in point because your systems are very flexible, whatever the default you want, you can customize the calculation dialog too. So if you've got a workflow that you're working on and you need to change the defaults, that's fine. We need to pick a default, and this is a convenient one, so that's what we've done. Okay, so enough about that. Let's go ahead and submit the calculation. I'll return to the calculations dialog just to show you what we're doing one more time, and I'm going to click the submit button from the lower right corner. I just want to point out, actually, before I do that, here I'll say okay. Before we submit, I'll point out that submit is also available from the setup menu as an entry, submit. So when you click the submit button, the first thing Spartan will do if you have not saved the molecule is prompt you to save it. In this case, the molecule exists in the SSPD, so Spartan is giving it a name, acrylonitrile. So I'm just going to accept that and save it. You'll get a little message that the job is running, and if I hurry and jump to the job monitor in the upper right, looks like sort of like a globe with a little EKG underneath it. We can watch a few optimization cycles before it finishes. Kind of like watching paint dry, but just to show you what's going on in the back end. Because I didn't minimize it, it took 5 optimization cycles. Probably had I minimized it, it would have come back in maybe 1 or 2. In any event, let's go and take a look at the output now that the job is finished. There was a little message dialog that came up that said the job had completed, and now we can go and take a look at the results. Let's look at results from the output dialog, Again, that is immediately to the right of the calculations dialog, output, or to the left of the properties dialog. You can also find the output dialog in the display menu, display output. Make this a little bit larger so we can see it. So this is a multi-tabbed dialog. So there are different entry points. We're in the summary in the upper left, and the information available is it's a summary, so it's pretty terse. It'll give you the version number, the job that was run, and then always available for QM calculations anyway should be orbital energies, atomic charges, and bond orders. And these are just little data tables, so you can click on these to expose them. And you'll see if you select other options in the calculations dialog, those will typically appear as data tables here as well. Okay, so the output summary, the standard output, this will again tell you the version that we're using. And we start, let's see, with the geometry optimization here. We'll give you the functional and the basis set. Okay, and then it'll just sort of walk through the iterative process of pushing energy in a sort of downward direction. We're trying to get to a local minima. So to optimize structure, to refine the angles and distances, it took 5 cycles and took something like 17 seconds on this box. Okay, also I should point out maybe this is an 8-thread box or an 8-core box, so the job runs in parallel. Okay, so data from the output, from either the summary or the output dialog. Let's go ahead and take a look at the properties dialog next. So we can do that. It's the icon immediately to the right of the output. It's the properties dialog here, also from the display menu, or you can always right-click on the background and choose properties. If you have nothing selected, the properties will be the properties dialog will be configured to display the properties of the molecule. If you click on something, whether it's a bond or an angle or a surface or a plot or something else, the dialog will change focus and will become the properties of the selected item. So with the molecule properties displayed, let's just take a look at some general properties that are available. Anytime, actually, firstly, I should mention, anytime you see this, it may be a little hard to see in the video, but this is a little downward arrow pointing. It's supposed to be like a post. This is a post button. Anytime you see the post button, it means if you click it, it will post the value into the spreadsheet. So the name, or for example, the energy of the highest occupied or lowest unoccupied molecular orbitals, the optimized energy, a dipole moment, etc. Anything that I click on, if I just go to the spreadsheet, you'll see that those have been posted into the spreadsheet. All right, I'm gonna close that. Okay. Also, I guess the dipole moment is available, but the vector is available too if you want to turn on a display. Actually, for this molecule, it's maybe a little bit easier to put this into a tube mode so we can see it. Okay, so you can display the dipole as well. Let's look at, we'll put this back in ball and spoke. Let's look at the atom properties dialog. So we were in the molecule properties dialog, and there are other tabs that I haven't looked at, and some of these are not currently applicable because we didn't request specific data from the calculations dialog. But let's look at the atom properties dialog. So let's just click on one of the carbons. Okay, so here you'll see the set of charges, electrostatic, Mulliken, and natural charges. These were also available under the summary. If I would have exposed this table, there's a data table with all charges as well, just to point that out. But you could post these values into the spreadsheet. Had we requested NMR, the calculated chemical shift would be available here as well. Okay, so from the properties dialog and in either under molecule properties or atom properties, you can grab additional information. Anyway, I guess I could click on a bond. We could look at the bond properties. It just gives you the length and then two calculated bond orders. Those are available to post into the spreadsheet as well. Okay, Now let's do one additional thing. Whenever you have a completed QM calculation, or if you've retrieved the molecule from the SSPD, you can immediately go to the surfaces dialog and request graphical models. If you've just built something, you'll need to have some data to build the graphics from. So you'll have to run a calculation to retrieve something from the database. But let's go to the surfaces dialog, either from the display menu or from the program icon or the dialog icon, and let's just add the electrostatic potential map. So under the add electrostatic potential map, and we looked at this recently. This is just a sort of a charge distribution map. So blue where I'm relatively positive, and red where I'm relatively negative by convention. Okay, and let me just do the following. I don't think we showed this before. We'll go back to the properties dialog, and I'm just going to move the surface off to the left and click on the actual surface, so that the properties dialog toggles to the surface properties. By default, Spartan uses red as negative, blue as positive, or relative negative and positive, depending on what the actual property that we're mapping is. But I should mention that there is also the option to modify the style. So if you don't want green in the middle, you can switch to white. I think other programs use this as a default, and that works as well. And you always have the option to turn on or turn off the display of bands. So if you want a nice blue, white, red image, that's available as well. And I should probably just mention, because I don't think I did this before, if you want a good quality image for export, just make the image as large as you can on screen, and just go to the file menu, and don't do a save as, do a save image as. And then from the save image as dialog, choose the PNG option. I think that's the default, and I'll go ahead and pretend I'm going to save this as a PNG file and say save. And then I'll be prompted, and you can choose the width, the height, so you can make it quite large if you like. And typically we do a transparent background. We don't take the background, but if you want to take the background, you can. That's up to you. And then you just say OK, and that'll save a good quality image to that location for you. Okay, so let's take a look at the next system, and I think that is cyclohexanone. Okay, so cyclohexanone, yeah, what we'll do is we'll build this, and then we'll run the default calculation, the equilibrium geometry calculation, and then we'll return, once that returns, we'll take a look at some calculated surfaces, so some graphical models that are predictive of reactivity. Okay, so firstly, let's go ahead and close this. Sure. Save, and then let's go. Actually, we'll do it as a sketch. Okay, and then let's set up a calculation. We'll just go to the calculations dialog, equilibrium geometry, density functional to default, and we'll just say submit, and then Spartan will want to give it a name. Cyclohexanone is fine, and we'll just say save, and we'll give a little indicator that the job is running. And sometime later we'll get a message that the job has completed, and we can now go and request some graphical models. Let's go in and take a look at firstly the lowest unoccupied molecular orbital. We'll do that because we know that the cyclohexanone molecule is susceptible to nucleophilic attack. So we figure as far as a nucleophile would be interested, it's going to be attracted to wherever the unoccupied, the lowest unoccupied orbital is typically. Okay, so what we'll do is we'll look at that, and we'll also look at the absolute value of the LUMO, the lowest unoccupied orbital, mapped on the electron density. So I went to the surfaces dialog, and that's available from the toolbar or the display menu, and we're going to add the LUMO, and we'll also go ahead and add the lowest unoccupied molecular orbital map at the very bottom, the absolute value of the LUMO mapped onto the electron density. Okay, Firstly, let's take a look at the LUMO. And this is a pi star orbital, and you can see it's concentrated primarily on the carbonyl carbon. Okay, so anti-bonding, and here I could click on it and make it transparent, just so you can, or mesh or something, so you can see underneath the hood. Okay, all right, and then let's take a look at the map. And we see it sort of extends above and below, sort of in the axial and equatorial phase. So we can ask the question: at which side am I more likely to want to attack from? Okay, so let's go turn this off. Turn off the LUMO, and then we'll turn on the LUMO map. Okay, and you can see there's one big blue spot up here on the axial face, which is definitely of interest to nucleophile, as the LUMO is concentrated there. And there's a lighter blue spot over here on the other face, on the equatorial face. So let's quantify that. Let's go to the properties dialog. And since I've clicked on the surface, it's the surface properties that will be displayed. If you've not, go ahead and just click on the surface to toggle to the surface properties. And you could bring up a legend if you want. The units are a little, it could be a little confusing. They're the square root of electrons per atomic unit cubed. But essentially we're looking at the units of the orbital, okay, mapped onto the density. But the piece, I guess the most important piece to point out is the highest concentration, or the biggest amount is on the axial phase. So if I'm a nucleophile, I'd be attacking from this side. And you can use the LUMO map in this way. It's useful when the systems are small, when the molecule becomes sort of too large, maybe sort of molecular weight over a couple hundred. The orbitals get spread out over multiple atoms. It's not quite as easy to see, but in small systems like this, it's very useful as a probe or as an indicator. Okay, so next let's take a look at, I don't know, what is next? Yes, that's right, the radical example. 3-cyano-4-methyl cyclohexenyl radical. Okay, I think we built this before in 2D, so this time I guess I'll do it in 3D just to demonstrate. Also, what we'll do is we'll run an equilibrium geometry calculation, but we'll need to take into account that there is an unpaired electron at this carbon. So we don't need to identify it at this location, but we need to note that there is an unpaired electron count change. So the default is 0, we'll switch to 1. Okay. Okay, so let's do this in 3D. Yeah, I guess it bears a tiny bit of narrating. Let's go cyclohexane, zoom in, rotate around so you can kind of see it. I'm going to make a double bond, and I'll do that from the bottom of the build panel. Click the minimize button just to clean the structure up. Okay, so let's say this is 1, 2 position over here. We're going to put the cyano group, so I'm going to delete. I held the delete key down to delete that bond. Click minimize to clean up again. I'm going to go to the groups menu, choose cyano, click here, rotate around, and then so roughly what is equatorial, I will put a methyl function at the 4 position. So 1, 2, so for the cyclohexene, 3, and 4. Okay, and this will be the location essentially where the radical is. If we were going to draw it in 2D, we would put it here. Okay, so go to the view mode, go to the calculations dialog, equilibrium geometry, neutral, and unpaired electrons. Here's where we'll make that change. Firstly, let me show you if I was to try and submit this without making the change. There's a little bit of spell check. Spartan says, hey, wait a minute, your molecule has either an invalid charge or an unpaired electron combination issue. So you say cancel here. And then you go and make an adjustment. So there's a little bit of a spell check to make sure that you don't submit something that doesn't make sense or that might be ambiguous. Okay, so we'll say enter and then submit. And we'll need to give this a name. All right, so Spartan doesn't recognize this. It's not in the database, so we'll need to give it a name and just say save. Okay, the job is running, and I won't show you how long it takes. It'll probably take a couple minutes to complete, but we can at least open up the job monitor while the job is running and take a look at the initial setup. Okay, so Spartan will initially calculate the wave function, okay, and then we're going to begin doing optimization cycles to sort of push energy downward. And the idea is we're pushing the potential energy surface gradient down to 0, and there we know we sort of found the minima. Okay, so after some number of 20 seconds or something like this, we're finished with an optimization cycle. And almost a minute in, we have a couple of optimization cycles. All right, about a minute 15 seconds for 3 cycles, so it's taken maybe 20 to maybe 30 seconds a piece. Okay, after a minute and a half, we have a 4th op cycle. Okay, and after some period of time, the job completes. All right, we can actually just take a quick detour and go see how long it took for the job to run. Okay, I went over to the spreadsheet and just added a little custom formula just to show you what that is. Anything on the left-hand side of the equal sign becomes the name of the column, and on the right-hand side is an expression et prop for properties and total wall time. So in minutes, the total job took 2 minutes, 2.1 minutes. So not too long, but long enough that you didn't want to watch it. Okay, now let's go and look at some graphical surfaces. So we can go to the surfaces dialog either from the toolbar in between the orbital energy diagram and the Spectra icon, or you can get there from the display menu. And in the case of surfaces, it's also actually available from the setup menu. So let's look at 2, maybe 3 indicators, I guess maybe 4 indicators of where is that single uncoupled electron in this system. Is it centered? Is it spread out across the entire molecule? Is it centered on one atom? Let's take a look. Okay, so what we can do, you'll notice a difference if you click the add menu from the surfaces dialog now. Because this was a uncoupled electron or a radical system, something with a different multiplicity than usual, we'll go and we have some additional items in the add menu. So let's choose spin density. And let's also choose spin density map, which will take the spin density and put that on top of the electron density. And I think we'll also look at maybe an orbital and a slice in a second. So first, let's take a look at these 2 surfaces. Okay, let's turn on the spin density. Okay, this is in electrons per cubic atomic unit, and you can see where the spin density is. It's delocalized, but it's definitely centered on specific atoms. Okay, so the nitrogen on the cyano group here. Let me make it mesh. Okay, so the nitrogen on the cyano group, and then a bit in the ring on these two ring carbons. Okay. And then let's look at the same thing, but a slightly different display. Let's take a look at the spin density map. So this is essentially the electron density. How close can I get to the system? And then map where the spin density is as it penetrates that, as it overlaps. And then one thing I'll say, sort of just looking at this right away, the typical scale would be red to blue. So it doesn't look like there's any red. So I guess I'm curious about it. So I'm gonna go to the properties dialog. And then with the properties dialog displayed, I'm just gonna click on the surface. And that will toggle the properties dialog to the surface properties. And you can see what the property range is, the default range. It actually looks like the min-max are kind of off range. At least, it's above the red. So let me click this reset min-max button. And this will put the scale on the absolute range calculated for this molecule rather than a default range. Okay, and here it makes it a little bit more obvious. The spin density is heavily concentrated over the 2 carbons that are on the ring, less so on the nitrogen out here. And this also sort of gives you an indication of where it is not on this ring carbon or these 2. I guess those are hydrogens, but in the carbons on the ring on this side either. Okay, same thing on the reverse. On the converse face. Okay, so now let's turn that off and let's go and take a look. We've seen the spin density before. Let me put this back actually in a solid display. And the reason I'm doing that is I'm going to go in and add what's called the alpha highest occupied molecular orbital, or the alpha HOMO. I'm going to turn that on and put that in a mesh mode, and you'll see that these basically trace the same thing. They basically answer the same question. One is looking at it from an orbital perspective and the other from a spin density perspective, but they're both answering the same question. Okay, and then one other way to sort of localize or visualize the spin or where that uncoupled electron is would be to look at a slice. So this is not under the add menu, but just adjacent to that, more surfaces. And then for the surface, way at the bottom, we're going to choose slice. And for the property, towards the bottom, we'll choose spin density. So we're going to take the spin density and we're going to take a slice of that. And then just say OK. And let me turn that on, and let me talk about what I've done. Okay, so we have a little plane that's been introduced, a slice. If you click inside the slice, it will select it. Or if your mouse skills are really good, you can click on the border if you can see it. Now you can use the center mouse wheel to zoom in. Okay, now this is at sort of an orientation. It may not be the best orientation, but it's at an orientation. So what I'm going to do is I'm just going to click outside of the plane, outside of the slice, and that essentially freezes the slice with regard to the orientation to the molecule. Okay, and now you can sort of see things if you wanted to try and make this a little bit more of a, try to make it a little more exactly slicing the plane of the ring, or as best you can, because it's not completely planar. You could rotate, and you also have the option you can translate and zoom as well. So with the here, let me make the actual molecule with everything selected. I zoom out, okay, to make the system smaller. I'll move this over to the left, and then I'll click within, and then I'll just zoom to make this a little bit larger. So this can give you a bit better visualization. Okay, it's not necessarily so easy to see, but blue again, it was the higher concentration. So again, around the nitrogen, blue again around the carbon, these two carbons in the ring. Okay, so 4 different ways to visualize essentially the same question, or answer the same question. Where is the uncoupled electron? Okay, let's look at the final example, which I believe is coumarin, and I think we'll do a UV-Vis calculation. Okay, so we will build coumarin. We'll do that in 2D, and we'll actually retrieve it from the Spectra properties database just to save a little bit of computational time, and that way we can do an energy calculation instead of an equilibrium geometry, because we'll already have the equilibrium geometry structure. And then we'll check the UV-Vis box, and we'll be off and running. Okay, so let's close what we have on screen. And go to new sketch, probably easiest to build in 2D. Okay, so build coumarin, we go into 3D with that. Let's go and take a look at the SSPD entry. Let's replace, and let's go set up a calculation. So energy, and then 1, 2, 3. So the fourth item down from in the left-hand margin, there's a row of buttons. So we're going to compute the UV-Vis. So just check this, and by default that will do the sort of the ground state and then the first 6 excited states. Spartan recognizes this as coumarin because we retrieved it from the SSPD. We know it's available, so we're going to say save, and we're off and running. And after, I don't know, maybe a minute and a half or a minute, something like that, the job will return. Okay, so now let's go ahead and take a look at the calculated UV-Vis spectra, and we can get there from the display menu Spectra, or you can grab the Spectra icon. It's just to the right of the surfaces and to the left of the spreadsheet icon. and then we'll click this plus icon to add, and then if you don't have UV-Vis highlighted, typically I think IR is highlighted. It's the fourth tab over. So UV-Vis will click calculated UV-Vis, and we can also, in this case, take a look at we'll click the add button again, and we'll add the experimental UV-Vis. And this comes from the NIST Chem Web book. They don't have a lot. One of the reasons we chose Qumran was because we knew it was in there. It would be an example we could use. There's something like maybe 2,300, 2,500 experimental UV-Vis spectra are available from the NIST website. Okay, so this will give you an indication of several different calculations. Once you've completed a calculation, you can add surfaces at any time. I guess I should also mention that you don't necessarily need to run the UV-Vis at the same time that you run, or the spectra calculation at the same time that you run your equilibrium geometry either, as we demonstrated by retrieving the equilibrium geometry from the database and then just doing an energy calculation to get the UV-Vis in this case. Okay, this will complete the introductory tutorials, and the next set of advanced tutorials, I think we'll do selections from those in a separate playlist, and that will be coming soon.